All right. Good morning, good afternoon, good evening for some of you. Welcome. My name is Tiffany Kataria. I'm the steering committee chair for the Exoplanet Explorers Science Series. So thank you for attending what is our second set of presentations for the 2023 cohort. As I begin all of these talks, I just want to give a brief overview of the program. So for those that aren't aware, the Exo Explorers Science Series, which is sponsored by the ExoPAG Executive Committee and NASA's Exoplanet Exploration Program, aims to enable the professional development of a cohort of graduate students and postdocs in exoplanet research that we've called Exo Explorers. Each member of the cohort will be featured in a webinar such as this that is live streamed to the exoplanet community, helping to increase their visibility within the field. The cohort will also learn from the experiences of established exoplanet researchers in the field that we've dubbed Exo Guides via a combination of tailored presentations and small group discussions. This third cohort is currently running from January 23 of this year till June of this year and is composed of 12 excellent early career scientists. So if you want to learn more information about the program and the cohort, one of our organizing committee members will be posting some links in the chat. So it's my pleasure today to introduce our two speakers, but before I do that, I wanted to set a few ground rules. So first, a reminder to behave professionally in this forum. Second, we plan to save questions until the end of each talk, so please either use the WebEx chat or the hand raise tool, which you should see either over your name. There's a high five icon. There's also a nice high five icon at the bottom of your WebEx screen. So let's go ahead and get started. So our first speaker today is Allison Duck. Allison Duck is a fourth-year PhD candidate at The Ohio State University. She received her bachelor's degree in physics and astronomy at the University of Maryland, College Park. Her research interests include transiting planets, stellar models, and planet demographics. She is also the lead instructor for the Polaris Peer Mentoring Program at Ohio State. The Ohio State. Her title today for her talk is Reanalyzing KELT 15b, an exploration of systematic errors in transiting exoplanets and their host stars. So with that, Allison, go ahead and take it away.
Great, I'll get my slides up. And there we go. Is it still working?
There we go. Yep, see it. I see it.
Okay, wonderful. Thank you so much. Yes, so I'm Allison Duck, and yeah, today I'll be talking about reanalyzing KELT 15b and exploring systematics, errors in transiting planets and their host stars. Many of the foundational questions we have in exoplanet science require precise and accurate parameters of transiting exoplanets. And these questions include things like understanding the underlying demographics of planets. We are mostly familiar with the Fulton gap, and that gap in radius between super Earths and sub-Neptunes that are dependent on really well-known radii of planets. And to be able to understand the interior composition of planets, again, requires really precise understandings of their radius and mass to understand their density profiles. And also to understand the atmospheric properties of planets, again, require precise understandings of their transiting and planetary parameters. However, in order to get those precise planet radii and masses and other parameters, we require precise stellar radii and masses, which becomes pretty clear when we think about the ways that we observe planets. So on the right, we have our on the left, we have our basic transit diagram, and on the right, we have a radial velocity measurement. And we can see that from transit, we get this nice proportion between the radius of the planet and the radius of the host star. And in radial velocity, we get a similar proportion, but for the mass of the planet and the mass of the host star. And we can combine information from these observations to get some pretty exciting parameters of the host star. Like we can determine the density of the host star just from parameters that are directly observable from transit and radial velocity measurements. However, this density is dependent on both mass and radius. We can't separate them out without including extra information. And that leaves the mass and radius of the host star as degenerate with the density, which we can make measurements of. And there's a couple different ways of breaking this degeneracy. We can take the example of the hot Jupiter host KELT 3. We can put constraints on the radius of the host star through broadband photometry measurements of its spectral energy distribution, as well as a parallax from Gaia to understand its distance to get the radius of the star. In the future, the SPHEREx mission will have more observations in infrared to further constrain that spectral energy distribution. and further constrain that radius. We can also take information from observations with tests of granulation. So we have stars that have pockets of hot gas flowing to the surface and then coming down, introducing flicker. And we can use that to understand the surface gravity of that host star to of order of 4% in surface gravity. And we can also use those constraints on stellar density that I mentioned earlier with test observations of the primary transit and a secondary eclipse to get densities of order 2%. There's also several other methods of constraining the mass and radius of the host star, like stellar evolutionary tracks and impairing scaling relations. And in this work, I have three primary goals. The first goal to analyze one system with 4 of these different methods of breaking the mass radius degeneracy in the host star, and then checking their agreement to see if they produce similar stars or similar planets. And then finally, quantify the systematic error introduced solely by the method selected for breaking this degeneracy between the mass and radius in the host star. Other work has been done in this field. In 2022, Jamie Teilhard and collaborators looked at 4 different stellar evolutionary codes and compared the results to each other and found a roughly 5% difference in the mass of the host stars and a 20% difference in the age of the stellar population, solely based on the stellar evolutionary code selected. In this work, I use stellar constraints that are more typically used for exoplanet studies. These include evolutionary tracks, so I also consider the MIST models, which are the MESA, isochrone, and stellar tracks. They're valid for a range of stars from about 1/10 of a solar mass to 300 solar masses, according to their initial paper, and thus can include some pre-main sequence stars and are based on a grid of initial masses and initial metallicities, as well as evolutionary phase. I also consider the YY isochrones, which are relevant for stellar masses of about 1/2 of a solar mass to around 5 solar masses. I also look at the Torres relations, which were developed by Torres et al. In 2009, based on a sample of 95 detached eclipsing binaries, where they were able to determine the mass and radii of these stars to about 3%, and then constructed a set of mass and radius relationships. And these are relevant for stars that fall within the high distribution point of their sample, which ends up being of about 1 solar mass to around 5 solar masses, with their sample being more sparse at either end of those ranges. And then finally, fitting a spectral energy distribution, like I mentioned earlier. So here we have an example for the star KELT 15, which is based on its flux at several different wavelengths, which you can see in the data points in red, and then fitting a model atmosphere for a star and having its theoretical outputs at different wavelengths, which are the points in blue. And then that can be combined with an estimate of the temperature and a measurement of its parallax to get a distance to fairly directly get an estimate of the radius of the host star. And this one can also be combined with the other stellar tracks that I mentioned before and mass radius relationships without double counting information. Now that I've got my 4 methods settled, I need my target. So in this work, we selected the KELT 15 to be the system that we reanalyze with all of these different methods. It's a roughly solar host star, about a G0. It contains a single hot Jupiter and was discovered by Rodriguez et al. In 2016 as part of the KELT survey program. And as part of KELT, it had some follow-up observations. So it had 3 sets of ground-based photometry, as well as 2 sets of ground-based radial velocity measurements shown below. However, my work has the benefit of occurring in the future. So we also have a suite of test observations from several different campaigns that we're able to incorporate in our work. Our first step was making sure that we could actually replicate the discovery results. So we don't include the test observations in this one. So this is the exact same photometry and radial velocity parameters used, or observations used, the exact same mass radius degeneracy breaking constraints. So we're both using the Torres mass radius relationships here, as well as, of course, the exact same target. In our work, we're using ExoFast version 2, which is an IDL-based code developed by Jason Eastman in 2012, and then updated to version 2 in about 2017, which is based on a Markov chain Monte Carlo, and it's able to simultaneously fit the planet and its stellar host. at the same time. So we're able to incorporate that information about the stellar density that we get from transit and radial velocity parameters when we're fitting the host star. It also jointly fits the transit and RV observations. And we're pretty happy with the level of agreement we get between these two runs. My work is shown in blue with the original discovery paper shown in orange. And again, we're fairly happy with the level of agreement, and we're able to move on to the next step of our work. So now we have our 4 methods and our system, time to analyze it. And in each time, we consider a default model, and a default model uses one of those 4 mass radius breaking constraints that I've listed. It assumes a circular orbit, and it also includes a prior on the stellar effective temperature based on high resolution spectroscopy of the target. And finally, it uses Claret limb darkening models to constrain our fits of our limb darkening parameters. And again, each fit is of the same same object, Kelt 15b, and uses the same transit and radial velocity observations, this now including the test data. For each iteration, we apply starting values based on initial SED fit to get a starting stellar mass and radius. We then incorporate all of our ground base and test observations. We select one of our 4 models listed here. And then finally, we iterate the MCMC until a Gelman-Rubin convergence score of 1.01 is achieved, and we consider our model converged. Now we can check agreement between all of our 4 of our models. And here's a distribution of our posteriors for several stellar and planetary properties. And there's just a couple I would like to highlight. So starting off, we have our distributions for the radius of the host star and the radius of the planet. So again, same system. The only thing that's changing is the method we're using to characterize the host star. And we see consistently that the MIST models are producing the smallest stellar radii, which through the depth of the transit gets translated to the smallest planetary radii. We also see that the SED constraint by itself is producing the largest stellar radius, as well as the largest planetary radius. This leads to a difference in our median values between the MIST and SED of about 6% or 2 sigma. So that means that the systematic difference caused just solely by model selection of your host star is at the level of twice the statistical uncertainty in any one model, making it a pretty significant source of systematic error. I'd also like to highlight, we do see a pretty significant bimodality in age in the MIST and YY models, which are only 2 models that give us age information. The SED and Torres models don't provide age information. And we see that bimodality in age being translated to a bimodality in mass of the host star. However, we don't see this bimodality or spread being translated to the mass of the planet itself. In this case, it's likely due to the relatively large uncertainty in semi-amplitude of our radial velocity observations, so that our masses are then clustered around one value. But I would assume that if we had higher precision in our semi-amplitude of our radial velocity measurements, we would see a similar level of spread that we see in the host star mass in our planetary mass estimates. Next, moving on to our combination constraint model. So that's taking, say, the MIST isochrone models and combining it with the information from the SED, as well as the YY and combining it with the SED, and then finally the Torres and combining it with the SED. And we see a similar level of spread in the radius of our host star, which is then translated to the radius of our planet. Here we see that spreads at the level of about 3% for these combination models between the smaller YY value here and larger MIST plus SED value here, which is about the same level as the statistical uncertainty in any one model fit. We also see that including the SED information changes our stellar effective temperature and density estimates. Since the SED does contain temperature information, we see that when combined with our stellar models, we see a larger spread in effective temperature than when it wasn't included in the single constraint models. And this effective temperature is impacting our limb darkening coefficients, which then impact our constraints on our more directly observable properties like the depth of the transit, which then does lead to a small shift in the density of the host star, which previously was completely consistent between all of the models. Now we see a slight shift based on these changes based on model selection. Then now we can quantify the systematic error introduced by the mass radius degeneracy breaking method. So this is putting all of those mass and radius constraints on one plane. So here we have the black line represents the density achieved by the MIST plus SED fit. And then we see that the MIST and SED really bookmark all of the runs that I've conducted, with MIST being the smallest and SED being the largest. Here in the center, we see the SED kind of falling neatly between the two. And then we see that the YY models are not shifted very dramatically by incorporating the SED information. And then finally, the Torres models do have a slight shift with the SED, but nowhere near as drastic as the MIST. And we also, it's important to point out that each of these density models are roughly consistent with each other, since they are primarily being driven by those directly observable parameters. So that's a good sanity check that even though when decoupling mass and radius, we're getting different values, that at least the density, which is being constrained by our observables, is being maintained. However, the choice of stellar model characterization is not the only source of systematic uncertainties when we're modeling these systems. I also mentioned 3 assumptions that we made when we considered each of our default models, that being assuming a circular orbit, providing a prior based on high resolution spectroscopy on the initial stellar effective temperature, as well as using the Claret limb darkening models. So we also consider iterations where we remove each of those starting assumptions. So trying a situation where we don't provide that prior on effective temperature, where we allow us an eccentric orbit, and when we don't constrain our limb darkening to the Claret tables. And here I'm showing the results of changing each of those assumptions. So let's zoom in on the Torres to start. So we have that red line showing the Torres default with a 1 sigma uncertainty band. That uncertainty band is the largest uncertainty for any of the 4 variations. And then we see the position of the point shows the difference between the median of the situation where we've changed an assumption and the default, of course, divided by the uncertainty. So for example, in the stellar density situation, we see a 2 sigma change, so that variation is twice the largest uncertainty away from the default value in the eccentric case, so we're not imposing in a circular orbit. This is especially interesting since all of our eccentricities that were produced are consistent with 0, but still by allowing the eccentricity to be fit and have an associated uncertainty, we do still see this shift in the in the density of the host star, which again is mostly considered or constrained by direct observables. And we see that shift is also translated to the density of our planet as well when we're allowing the orbits of the planets to be eccentric. Moving on to highlighting some of the results that we see in the MIST variations, we see fairly consistent stellar densities, but we do see a shift in the measured depth of the transit delta when we are no longer using the Claret tables, which is associated with a small shift in the density of the host star, showing that even some of these things that we consider just direct observables can be impacted by these assumptions that we're putting into our models. Moving on to our combination constraints, we see that when we consider MIST plus SED, we're seeing another large shift in the density of the host star, again, based on letting the orbits be eccentric, even though, again, that eccentricity is 0. And similar levels of shift in the depth of the transit and ingress and egress time of the transit based on whether or not we were using the Claret limb darkening tables. And then in the YY plus SED, we see a significant shift in the derived effective temperature when we're not including that extra temperature information, which then leads to shifts of about 1.5 sigma in both the mass of the host star and the radius of the host star, which is also translated to the radius of the planet, showing that these assumptions that we're putting into our models at the start can also have significant levels of systematic uncertainty. This kind of highlights the need for consistent modeling practices. So we know that there are significant contributions of systematic error from model choice alone, which can be up to twice the statistical uncertainties. And understanding a detailed choice of our prior introduces additional systematic uncertainties at the same time, at the same magnitude as our statistical uncertainties. So both the model choice and associated priors can have significant systematic uncertainty effects. There's also some other benefits from reanalyzing these systems. For example, in this case of KELP 15b, we were able to significantly improve the precision on the period by about 50% in this case. So in this red cone that gets larger over time is the initial uncertainty associated with the period based on the original discovery paper in 2016. And then now with the benefits of the long baseline between those initial discovery observations and the new test observations, we've been able to constrain the uncertainty in that period to the blue cone to the point where it's well contained within the duration of the transit, represented by this purple oval. And to the point where this object would have been completely unobservable by a future mission like Ariel, which would be launched in 2029 and hopes to characterize the atmospheres of transiting hot Jupiters. It would have been many times the duration of the transit eclipse. And it's now well within their requirements of transit precision of about 1/12 the transit duration in order to decrease that overhead in these missions. We've also identified about 80 hot Jupiters to be reobserved with tests that would benefit from the additional observations to refresh their ephemerides. We're also not the only researchers interested in this work. Diana Dragomir in 2020 highlighted that in a simulated sample of test planets, about 81 would have had their ephemerides expired after over a year and would be difficult to reobserve. And similarly, Rob Zelm in 2020 with collaborators showed that citizen science observations are an important tool in refreshing these ephemerides. So there's benefits in not only refreshing the ephemerides of these targets by incorporating additional observations and reanalyzing them, but we could also be introducing these increased awareness of systematic uncertainties. These applications also not only relevant to exoplanets, but also could be potentially important for M-dwarfs as well. We looked at two M-dwarf systems that had a FGK companion star, and the M-dwarf transited in an eclipse. And we found that when we reanalyzed these M-dwarfs with the Torres plus SCD, YY plus SCD, and MISS plus SCD, that we found a similar 3% spread in radius based on which model we selected. And that leads to then another important consideration when we're trying to derive the radii of these M-dwarfs, that we need to consider these systematic uncertainties. This was not at the level that this would solve the M-dwarf radius inflation problem, where we see that the measured radii of M-dwarfs tend to be larger than what we would expect from evolutionary models, but it's still an important consideration in their overall error budget. In the future, I hope to reanalyze a sample of exoplanet host stars with interferometrically measured radii. Often when I tell people about my results, the first question I get is like, okay, great, you've compared all of these models, which one should I use? Which is a difficult question to answer since I've been able to see that the models don't disagree with each other, but I haven't been able to actually fly out to the star with the measuring tape to get the exact correct radius. But one way we can compare to something like a fiducial is looking at a sample of interferometrically measured stars. That way we can quantify the systematics I've measured here, but compared to a fiducial where we have a better idea of what the right answer should be. Also in the future, I hope to reanalyze a larger sample of hot Jupiters with consistent methods so that this sample would have similar levels of systematic errors and updated ephemerides from recent observations with tests. And it could be a sample that could be more directly compared for demographic studies due to similar systematic errors. In conclusion, in order to make meaningful comparisons between planets, we still need a full understanding of their error budgets. There is significant contribution from systematic errors from model choice, up to 6% or twice the statistical uncertainty. And we also encourage exoplanet researchers to consistently report which mass radius degeneracy breaking method they're using to characterize their host stars, so we can eventually compensate for some of these systematic uncertainties. And in the future, I hope to apply this method to a larger sample that would have consistent systematics, and well as compare each of these models to something like a benchmark system. And thank you all very much for your time.
Thanks so much, Allison, for a great talk. All right, any questions? So again, feel free to use either the WebEx chat or if you want to raise your hand. All right, let's see. We've got a couple of questions, I think. Okay, Sean, go ahead and ask your question. Oh, Sean, you there?
I also can't see the chat. I don't know where it went when
I'll read it to
to
you.
full
It's
screen.
fine.
Thank
No
you.
worries. Yeah, no problem at all. Yeah, I know the WebEx interface can be stressful sometimes. Sean, I don't know if you're unmuted, but I can't hear you. So maybe if you want to go
How
ahead and
about
jump
now?
in. Yes, now
All
I
right,
can hear
sorry
you.
about
Great.
that.
Go
Thank you.
ahead.
Great talk,
No
Allison.
worries. Go ahead.
Thank you.
Great talk, Allison. In your opinion, how big of a problem is this for people trying to use good measurements of planets in their studies? This difference in the model choices that are being used and it not being reported at all. Is this tragic for people working with this data or no?
I would say that it's definitely an important consideration to consider. And if you're seeing radii better than like honestly better than like order like 4 to 5%, then I would have some questions about how they determined them. So it was more a call for increased credulousness around really precise planetary properties, since we do have to be including these systematic errors. So I do think if you see something with a like suspiciously small error bars, you could probably know that then like, oh, you have to add in systematic uncertainty. But I would be extremely cautious about taking some parameters at face value that haven't addressed this part.
Thanks, Sean. Any other questions? There were like some hand raises that went off and then went down. So again, feel free to use either the chat or the hand raise. All right, Rob, go ahead.
Yeah, Allison, really great talk. Thank you so much for that. So I love how the next step is to look at interferometry data to sort of see if we can compare, or really you guys, compare the measured radii from that method, compare to what you're getting from your methods. But what happens if there's a target that you have on your list that doesn't have interferometry data? Can you do this for any star that has been observed by these telescopes, or do you need a specific population subset that this works on?
So this comparison method we can do with any star that has observations in transit or radial velocity. Each of the 4 methods that I've talked about in this talk are all implemented in ExoFast version 2. So as long as you have data that you can fit, you can compare a star with each of these 4 methods. For the next step with comparing to interferometry, we're hoping to compare to something like a baseline or fiducial to answer in which situation or which of these models better, where we do need some increased information about the star. But if you wanted to have an understanding of how much a systematics of this type would apply for a certain system, you can definitely analyze them with each of the 4 methods. And at least for the 4 that Jamie Tayar and collaborators analyzed, they wrote a code that produces an estimate for at least the 4 stellar evolutionary models they looked at. And I kind of used this system as a placeholder for a lot of typical hot Jupiter systems that have maybe a number of transit observations, a couple RV observations, but is otherwise a fairly typical hot Jupiter. So I would expect systematics to be at a similar level.
Cool. Thank you so much.
That
Looking forward
answers
to
your
seeing
question.
yeah, and looking forward to seeing the next phase of your research and reading your paper. Good luck on the referee process. Thanks again.
Thank you.
Great. All right. Well, with that, let's thank Allison again, and then we'll move on to the next speaker. Allison, maybe if you want to drop your email in the chat if folks have additional questions.
Thank you so much.
Yeah, thanks.